It's Hello friends, it's Relativistic here, and today we are going to discuss about relativistic total energy. This is the relation, this is the expression of relativistic total energy, and I'm going to show you how to derive this equation. And please subscribe the channel before we start, and hit the thumbs up button. Also share with your friends, inspire me to create new content for you, and also help me to grow my channel. So now let's start. Suppose a particle of mass m is is moving with velocity v, and it experiences force F is equal to, let me write here, suppose a force which is F, which is equal to, let me write this way, which is equal to time derivative of m into v, where m is the mass, v be the velocity. Okay, b acting on a particle, okay, acting on a particle, right? And particle of mass m, okay, particle of mass m, particle of mass m, mass m, particle of mass m. Okay, now you see v is the velocity here. Okay, v is the velocity here. Now you see, when this force displaces the particle, okay, when this force displaces the particle, through a very small distance, through a very small distance, let me write it clearly, okay, small distance dr, small distance dr, in the direction of the force, in the direction of the force, in the direction of the force, then gain in kinetic energy, then kinetic energy gained, okay, kinetic energy gained is equal to work done by the force F to displace it through dr. So what does it mean? That means, so this is the particle of mass m. When this force F acts on it, if it displaces through a very small distance dr, then work done to displace it through dr will be equal to the kinetic energy gained by this particle, right? So hope you have understood this. Now you see, so this kinetic energy gained when it is displaced through a very small distance, there is a very small increase in kinetic energy. Let me represent it by dEk, which where Ek represents kinetic energy. dEk means very small gain in kinetic energy, right? And now work done is force into displacement. So here generally we used to write force dot product of force and displacement. So F dr cos theta. Here you see I have written the distance. It is displacement. It is displaced through a very small distance in the direction of the force. So displacement and the direction of the force and displacement same. So cos 0, that's going to be 1. So that's why simply we can write F into dr, right? Hope it's clear to you. Right, now you see this force is equal to this one, right? So here I am writing this mass m. Don't write the mass outside thinking that mass is constant here. In case of relativity, in case of relativistic mass, this mass cannot be taken as constant, right? So here we're gonna put dt of m into v dr. Now what we can do here, we can write dr by dt and dmv. We can write dr by dt and into dm into v. We can write that way. And dr by dt is nothing but velocity, right? dr by dt is nothing but velocity v. Okay, so we have got v into dmv. That's what we have got. So since v is equal to dr by dt, simply dr by dt, right? So hope it's clear to you. Now you see, if we consider the initial velocity is 0, if the particle starts from 0, if the particle starts from 0, starts from v is equal to 0 and acquire a velocity v. Okay, so it starts from velocity 0 and acquire a velocity v. Then in that case acquires a velocity v. So let me, okay, acquires a velocity v. Then you see, in that case total gain in kinetic energy, then gain in kinetic energy is given by Ek. That's going to be integration dEk, because this is small gain in kinetic energy when the particle was displaced through a very small distance, right? And if you integrate this from 0 to v, velocity increases from 0 to v, right? What was dEk? That was this, we can put this, right? v dmv, right? If we integrate this, if we integrating by parts, if we use product rule, integrating by parts, then what we're going to get? A first function derivative of the second function dmv, right? Now if you integrate this, then it's going to be mv. So let me write here direct mv, and here we are integrating it from 0 to v. So 0 to v minus, then derivative of the first function, derivative of this first function is dv, then integration of the second function, that means integration of dmv, that's going to be mv again, right? So that's equal to 0 to v, right? So now you see, let me write this one in this way. Let me write this one in this way. MV dV. We can write this way, right? MV dV. Now if you put the upper limit, then subtract whatever value you get putting the lower limit. Put upper limit and lower limit, then what are you gonna get? You're gonna get the same value. You're gonna get v minus 0, that's gonna be again vmv, that is v square, right? If you put the upper and lower limits here, that's gonna be v into v, again we're gonna get v square, right? So that's why we can write m v square minus integration from 0 to v mv dv. So this is what we're gonna get. This is kinetic energy, right? So now let me clean these things. Okay, let me keep this equation. We're gonna continue from here, right? So pause the video and note it down. I'm gonna clean this board. So we have got this equation. Now let me integrate this part. Before that, let me put this relativistic mass m is given by m is equal to m naught by root over 1 minus v square by c square, right? We know that. So if we put this one here, so if we put this here, then we're gonna get m naught v square by root over 1 minus v square by c square, right? And minus integration 0 to v, instead of m we're gonna put m naught here, v dv divided by root over 1 minus v square by c square. That's what we have got. And here m naught is rest mass, right? M naught is rest mass. So now here you see, let's integrate this part, only this part. So first let me show you how to integrate this part. Okay, so let me divide this board, and here you see, first let us consider that first, just wait, what we need to do, we need to find the integration of m naught v dv by root over 1 minus v square by c square. Let's integrate this. Okay, now in order to integrate this, let us consider that 1 minus v square by c square is equal to, suppose let it be, suppose t. Let us consider it is t. Instead of t, let me take this one as another thing. Let me take this one as x. Okay, let me take this one as x. So if you differentiate both sides with respect to x, differentiating with respect to x, then here derivative of 1, that's going to be 0, minus derivative of v square, sorry, not with respect to x, with respect to v. Let us divide both sides by with respect to v. Then v square, that's going to be twice v, c square is constant, and here it's going to be dx by dv, right? That's what we're going to have. So if you simplify this, then what you're going to have, you're going to have that's supposed to be v, okay, dx by dv. So here minus 2v dv by c square is equal to dx, and so what we're going to get, v dv, that's going to be equal to minus c square dx by 2. That's what we're going to have, right? So hope you can see it clearly. One more thing, if you consider that 1 minus v by v square by c square is equal to x, and if you integrate this now 0 to v, instead of writing 0 to v, we have to change these limits. Now we have considered this part is x, root over x, m v dv, instead of v dv we're going to write minus c square by 2 into dx, and constant part, let me write that one outside. This is m naught. So m naught can be also taken outside. Rest mass is constant. Okay, so it can be taken outside. So c square m naught by 2, that is written outside. Here minus is also written outside. Then dx, let me write here dx. Now what will be here, the upper and lower limits here in this case. Now you see, when you put here, v is equal to 0, when you put v is equal to 0 here, then x gonna be 1. For v is equal to 0, x is equal to 1. If you put 0 here, that's going to be 1. And for v is equal to v, and this x going to be equal to 1 minus v square by c. That is what we have considered, right? So that's why this limit should be, instead of 0, we have to put 1, because now we have replaced this by x. So here we're going to put x is equal to 1, and here we're going to put x is equal to 1 minus v square by c square. That's what we're going to put, right? So here is this is the lower limit now, and this is the upper limit. Okay, this is what we have got. So hope you have understood this. Now if you integrate this, now you see integration of dx by root x. So root x is 1 by root x is x to the power minus half, and if you integrate this, then it's going to be minus half plus 1 by minus half plus 1. That's what we should get, right? According to this formula, x to the power n dx, x to the power n dx is equal to x to the power n plus 1 by n plus 1, and this is nothing but integration x to the power minus half dx, right? If you integrate this, then you're supposed to you should get this using this formula. So if that is the case, then it's going to be equal to minus half plus 1 is plus half, x to the power 2, and here also half. That's what we're going to have, right? Hope you have understood this. Now if that is the case, then here we will get minus c square m naught square by 2. Then here we have got x to the power half. X to the power half means you can write root x divided by half, and let me clean these things. Okay, divided by half, and we are integrating it from 1 to 1 minus v square by c square. That's what we have got, right? Hope these things are clear to you. Then these 2 cancels these 2, right? So we can write minus m naught c square minus m naught c square, and if you put the upper and lower limits, then what you're gonna have, if you put this one here, you're gonna get root over 1 minus v square by c square, and let me write within bracket. Then if you put the lower limit, that is 1, then you're gonna get here 1. That's it. Okay, so hope you have understood this. Now let me clear one more thing here. So what we have written here, this one, so instead of v, now you see, let me tell you again, when we have substitute this by x, then these 2 should be also changed, right? So for x, we have considered x is equal to 1 minus v square by c square. So that means, so if you replace this one by x, then when v is equal to 0, if you put here 0, when the lower limit is 0, then you see 1 minus 0 square by c means 0, then 1 minus 0 is 1, so x becomes 1, right? So for v is equal to 0, x becomes 1. Now for v, upper limit v, that means this v remains v, then x will be equal to this one. So we have used here as the upper limit 1 minus v square by c square. So actually we have to use this upper limit, okay, in this case when you replace this by x. Okay, so hope you have understood this. And lower limit become 1, because for v is equal to 0, x becomes 1, x becomes 1, for v is equal to 0, and for v is equal to v, then x becomes 1 minus v square by c. That's why instead of v we have written here 1 minus b square by c square. Then here we have used the integration formula. So now we have got the we have got the result of this integration, this part, right? Now let us replace this part by this result. This is the result of this one. So now let us replace this. So if you do so, then what you gonna get? Ek is equal to m naught b square by root over 1 minus b square by c square minus, and there is also minus, so it's gonna be plus m naught c square within bracket root over 1 minus b square by c square minus 1. That's what we're gonna have. Okay, so now open this bracket. Let me simplify. M naught b square by root over 1 minus b square by c square plus m naught c square into this root over 1 minus b square by c square. Then again this one into minus 1. That's going to be minus m naught c square, right? And from these two, what we can do, you say, just wait. Okay, in this case, just here you see, we can simplify this like this. Let me simplify this one. So what you're gonna have, okay, right, let me take this one as if you take this LCM and m naught common, m naught is taken as common. Okay, m naught is taken as common. Then if you take the c naught, if you take the c square common, not c naught, c square common, then this b square, so here there is no c square, there is b square, so that's why after taking common this term will be b square by c square, right? Because we have taken c square also common. Here we have c square but not here, right? 1 by root over 1 minus b square by c square, then plus, and these two common, we have 1 minus b square by c square. Okay, so now bracket close, minus m naught c square, minus m naught c square. Okay, now you see, let me clean this part. Already we have used this. Okay, now you see, let me simplify this. Okay, so if we simplify, then what we're gonna have, Ek total energy, kinetic energy, total kinetic energy will be. So if you take this LCM, then what you're gonna have, you're gonna have m naught c square, and here we have b square by c square, then root over 1 minus b square by c square is the LCM here, and if you multiply this one with this one, then root will be removed, plus 1 minus b square by c square and minus m naught c square. That's what we're gonna have. Now you see here, this and this cancel, one is positive, another is negative, so we end up getting Ek is equal to m naught c square by root over 1 minus b square by c square minus m naught c square. That's what we have got. This is the kinetic energy, right? Now you see, pause the video and note all these things. I'm gonna clean this board, left part. Okay, see, this quantity m naught c square, this quantity m naught c square is called rest mass, is called rest mass energy, rest mass energy. Okay, rest mass energy. And the total relativistic total energy, relativistic total energy is E is equal to kinetic energy, that is Ek, that we have already got, plus rest mass energy. Let me consider this as rest mass. Okay, E naught. This is E naught, rest mass energy. Kinetic energy plus rest mass energy. Rest mass energy. Adding these two, we're gonna get the total relativistic energy. So if we add these two, that is m naught c square by root over 1 minus v square by c square minus m naught c square plus the rest mass energy is m naught c square. So here m naught c square minus m naught c square plus m naught c square, these two cancels, right? These two cancels, minus m naught c square cancels, plus m naught c square, right? These two cancels, and so we end up getting m naught c square root over 1 minus v square by c. So this is the expression for relativistic total energy. Or we can write E is equal to m c square, because m is equal to m naught by root over 1 minus v square c square, which is already mentioned earlier in this video, right? So hope you have understood this. This m is nothing but m naught by root over 1 minus v square by c square, which is already mentioned earlier, right? So this is the required expression, either this or you can write in this form, right? So if you want to know the relation between this energy and momentum, relativistic energy and momentum, then there is another video that I have already made on the topic, which is whose link is in the description box. You can watch that video. Okay, so if you want to express this energy in terms of momentum, then you can watch that video, right? So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.